Hi, my name is Lynn McTaggart. Welcome to my podcast, Living the New Science. In these first podcasts, I'm covering some extraordinary discoveries by frontier scientists and why this changes everything we think about how our world works and also how we should live our lives. It also gives you a full understanding of why the world out there is mutable and can be affected by our thoughts. Today, I want to tell you about an extraordinary, groundbreaking experiment that shows us how interconnected everything is. I've been looking for evidence of ways in which the components of our physical universe, which we think of as fully realized, are capable of being fundamentally altered, particularly by the power of a thought. It's also important to find evidence that quantum behavior, like the observer effect, which I've described in earlier podcasts, occurs outside the subatomic world, in the world of the everyday, the big sticks and stones world that we know. The experiment I want to tell you about was carried out by a distinguished professor of physics at the University of Chicago named Tom Rosenbaum. Rosenbaum was ahead of the curve, one of a small group of experimental physicists who liked to study the inner workings of liquids and solids when their underlying order was disturbed. In physics, if you want to find out how something behaves, the best way to do it is simply to make it uncomfortable and then see what happens. Creating disorder in a solid or liquid usually involves adding heat or applying a magnetic field to see which spin or magnetic orientation that the atoms will choose. Most physicists studying condensed matter physics are interested in symmetrical systems where atoms are arranged in an orderly array, like eggs in a carton. But Rosenbaum was drawn to strange systems that were inherently disordered, which more conventional quantum physicists like to refer to disparagingly as dirt. Rosenbaum believed that dirt offered the unprobed secrets of the quantum universe, uncharted territory that he was happy to navigate. He particularly liked substances called spin glasses, which are strange hybrids of crystals with magnetic properties. Unlike an ordinary crystal, whose atoms point in the same direction in perfect alignment, the tiny magnets associated with the atoms of a spin glass are wayward and frozen in disarray. Atoms and subatomic particles never stop moving, so when you want to study them in physics, you need to slow them down. And the way to do it is to make them cold. The use of extreme coldness allows physicists like Rosenbaum to slow down the atoms of these strange compounds enough to observe them minutely and to tease out their quantum mechanical essence. At temperatures near to absolute zero, when their atoms are nearly stationary, they begin taking on new collective properties. Rosenbaum was fascinated by the recent discovery that systems that are disorderly at room temperature will suddenly become much more conformist and act far more alike once they're cooled down. To study these atoms, Tom Rosenbaum got hold of a helium dilution refrigerator. Temperatures in the refrigerator, which was a boiler-sized circular apparatus with a number of cylinders, can descend to a few thousandths of a degree above absolute zero, which is around a minus 459 degrees Fahrenheit, which is almost 73 degrees centigrade below freezing. So that in itself is 3,000 times colder than the farthest reaches of outer space. Without heat of any description, the atoms in matter can slow to a crawl. At this scale of coldness, the universe would grind to a halt. It's the scientific equivalent of hell freezing over. Examining how molecules behave as a group in various circumstances is highly instructive about the essential nature of matter. There at these lowest temperatures where everything occurs in slow motion, the true nature of the most basic constituents of the universe may well be revealed. According to the second law of thermodynamics, all physical processes in the universe can only flow from a state of greater to lesser energy. We throw a stone in a river, and the ripple it makes eventually stops. A cup of hot coffee left standing can only grow cold. With this idea, things inevitably fall apart. Everything travels in a single direction from order to disorder. But this might not always be inevitable, Rosenbaum believed. Recent discoveries about disordered systems suggested that certain materials, under certain circumstances, might counteract the laws of entropy. In fact, they might come together rather than fall apart. He wondered whether it was possible that matter could go in the opposite direction, from disorder to order. For 10 whole years, Rosenbaum and his students at the James Franck Institute had been asking just that question of a small chunk of lithium holmium fluoride salt. Rosenbaum had inside his refrigerator a perfect chip of rose-colored crystal, no bigger than the head of a pencil, wrapped in 2 sets of copper coils. He'd chosen these dazzling little specimens because they were one of the most naturally magnetic substances on Earth. But first, he had to make this crystal even more disordered. So, what he did was to have the lab that grew the crystals combine holmium with fluoride and lithium, the first metal on the periodic table. The resulting lithium holmium fluoride salt was predictable, a highly ordered substance whose atoms behaved like a sea of microscopic compasses, all pointing north. Rosenbaum then asked the same lab to rip out a number of the atoms of holmium bit by bit and replace them with yttrium, a silvery metal without such natural magnetic attraction, until he was left with a strange hybrid of a compound, a salt called lithium holmium yttrium tetrafluoride. By virtually eliminating the magnetic properties of the compound, Rosenbaum eventually had a Frankenstein monstrosity whose atoms pointed any way they liked. With these new spin glass compounds, Rosenbaum could virtually change the properties of the compound at will. He could make the atoms orient in a particular direction or freeze them in some random pattern. However, Rosenbaum's holmium compounds behave themselves in some regards, but not in others. One thing he couldn't do was to get them to obey the laws of temperature. No matter how cold Rosenbaum made his refrigerator, the atoms inside them resisted any sort of ordered orientation. It was a little like an army refusing to march in step. Working with Rosenbaum was one of his star PhD candidates called Cy Ghosh, a slight 23-year-old who'd won a coveted physics prize, only the second woman to do so since its inception 25 years before. According to the laws of classical physics, applying a magnetic field will disrupt the magnetic alignment of a substance's atoms. The degree to which this happens is the salt's magnetic susceptibility. The usual pattern with a disordered substance is that it will respond to the magnetic field for a time and then plateau and tail off as the temperature drops or the magnetic field reaches a point of magnetic saturation. The atoms will then no longer be able to flip in the same direction as that of the magnetic field, and so will begin to slow down. In Cy's first experiments, the atoms in the lithium holmium yttrium salt, as predicted, grew wildly excited with the application of the magnetic field. But then, as Cy increased the field, something weird began to happen. The more she turned up the frequency, the faster the atoms continued to flip over. What's more, All the atoms, which had been in a state of disarray, began pointing in the same direction and operating as a collective whole. Then small clusters of about 260 atoms aligned, forming oscillators, or spinning collectively in one direction or another. No matter how strong the magnetic field that Psi applied, the atoms remained stubbornly aligned with each other, acting in concert. This self-organization persisted for about 10 seconds. Rosenbaum decided to carry out another experiment to attempt to isolate the property in the crystal's essential nature that had enabled it to override such a strong outside influence. He left the study's design to his bright young graduate student, suggesting only that she create a computerized, three-dimensional mathematical simulation of the experiment she intended to carry out. In experiments of this nature on such tiny matter, physicists must rely on a computerized simulation to confirm mathematically the reactions they're witnessing experimentally. The plan was to find out a bit more about the salt's magnetic capability by applying two systems of disorder to the crystal chip: higher temperatures and a stronger magnetic field. Psi planned to measure the magnetic susceptibility and the direction of spin of the individual atoms. A connection attached to her PC would enable her to change the voltage, the magnetic field, or the temperature, and would record any changes whenever she altered one of the variables by the tiniest degree. She began lowering the temperature a fraction at a time and then began applying a stronger magnetic field. To her amazement, the atoms kept aligning progressively. Then she tried applying heat and discovered they again aligned. No matter what she did, in every instance, the atoms ignored the outside interference. Although she and Tom Rosenbaum had flushed out most of the compound's magnetic component, of its own volition, as it were, it was turning into a larger and larger magnet. That's strange, she thought. Perhaps she should take more data just to ensure they'd encountered nothing strange in the system. She repeated her experiment over 6 months until the early spring of 2002, when her computer simulation was finally complete. One evening, she mapped out the results of the simulation on a graph and then superimposed the results from the actual experiment. There on the computer screen was a perfect duplicate. The diagonal line formed from the computer simulation lay exactly over the diagonal line created from the results of the experiment itself. She'd even mapped out where the atoms should have been on the graph had they been obeying the usual laws of physics. But they weren't in any sense. There they were in a line, a law completely unto themselves. The following day, she and Rosenbaum examined her graph. There was no other possibility, they both realized. The atoms had been ignoring her and instead were controlled by the activity of their neighbors. No matter whether she blasted the crystal with a strong magnetic field or an increase in temperature, the atoms overrode this outside disturbance. The only explanation was that the atoms in the sample crystal were internally organizing and behaving like one single giant atom. All the atoms, they both realized with some alarm, must be entangled. One of the strangest aspects of quantum physics is a feature called non-locality, also rather poetically referred to as quantum entanglement. The Danish physicist Niels Bohr discovered that once subatomic particles such as electrons or photons are in contact, they remain aware of and influenced by each other instantaneously over any distance forever, despite the absence of the usual things that physicists understand are responsible for influence, such as an exchange of force or energy. When entangled, the actions, for instance, the magnetic orientation of one subatomic particle will always influence the other in the same or the opposite direction, no matter how far they're separated. Erwin Schrödinger, another of the original architects of quantum theory, believed that the discovery of non-locality represented no less than quantum theory's defining moment, its central property and premise. To understand entangled particles, imagine you've got a set of twins separated at birth. One lives in Colorado and the other in London. Although they never meet again, both like the color blue, as it turns out. Both take a job in engineering. Both like to ski. In fact, when one falls down and breaks his right leg at Vail, Colorado, his twin breaks his right leg at precisely that same moment, even though he's 4,000 miles away sipping a latte at Starbucks. With quantum particles, once they're entangled, it's like they retain a telepathic connection forever. Albert Einstein refused to accept non-locality, referring to it disparagingly as spooky action at a distance, because it violated his theory that nothing travels faster than the speed of light. Nevertheless, modern physicists have demonstrated decisively that the speed of light is not an absolute outer boundary in the subatomic world. Although even the most conservative physicists now accept non-locality as a given feature of the quantum world, they console themselves by maintaining that this strange, counterintuitive property of the subatomic universe doesn't apply to anything bigger than a photon or an electron. Once things get to the level of atoms and molecules, which in the world of physics is considered macroscopic or large, the universe starts behaving itself again according to predictable, measurable Newtonian laws. But with one tiny thumbnail's worth of crystal, Rosenbaum and his graduate student demolished that delineation. They demonstrated that big things like atoms were also non-locally connected, even in matter so large you could hold it in your hand. Never before had quantum non-locality been demonstrated on such a scale. Although the specimen had only been a tiny chip of salt, to the subatomic particle, it was a palatial country mansion housing 1 billion, or 10 to the 18th power, worth of atoms. Rosenbaum, ordinarily loath to speculate about what he couldn't yet explain, realized they'd uncovered something extraordinary about the nature of the universe. And to me, Rosenbaum and Gauss had discovered a mechanism for intention. They demonstrated that atoms, the essential constituents of matter, can be affected by non-local influence. Large things like crystals aren't playing by the grand rules of the game, as Richard Feynman, the famous physicist, called the big rules of modern Newtonian physics, but by the anarchic rules of the quantum world, maintaining invisible connections without any obvious cause. Gauss's research, in my mind, represents two defining moments in modern physics. Her experiments show that an invisible connection exists between the fundamental elements of matter, which is often so strong that it can override classical methods of influence, such as heat or a push. This experiment was among the first evidence that the peculiar properties of quantum physics don't simply occur at the quantum level with subatomic particles, but also in the world of big visible matter. It showed that molecules also exist in a state of pure potential, not as a final actuality. Under certain circumstances, they escape Newtonian rules of force and display quantum non-local effects. The fact that something as large as a molecule can become entangled suggests that there aren't two rule books, the physics of the large and the physics of the small, but only a single rule book for all of life. What Rosenbaum had discovered in his refrigerator might offer some vital clues as to how every object or organism in the physical world, which classical physics depicts as an irreversible fact or a finalized assemblage only changeable by the brute force of Newtonian physics, could be affected and ultimately altered by the energy of a thought. The big idea here is how this experiment holds the key to a science of intention, how thoughts are able to affect finished solid matter. The physical world, matter itself, appears to be malleable, susceptible to influence from the outside. So here's a little experiment to test out non-locality in your world. Scientists like the Institute of Noetic Sciences' Dean Radin and British biologist Rupert Sheldrake have exhaustively studied the sense of being stared at, the fact that we can often intuitively sense that we're being stared at. Ask a friend to work with you. Place 2 chairs in a room, one with its back to the other, so that when you're sitting in the one behind, you will be able to see your partner, but he or she won't be able to see you. Both of you need a timer. There's usually one on your smartphone, plus a piece of paper and pencil. You, as the starer, should begin by not looking at your partner, who has his or her back to you, of course. At random intervals, stare at her. Whenever you do, check your timer and write down the exact minutes and seconds you began staring. Your partner, meanwhile, should write down any time with minutes and seconds she has a strong sense of being stared at. After 15 minutes, stop and compare notes. If one or more of your timings have correlated, you will have demonstrated that we are all connected non-locally by an invisible web. Switch roles and compare notes. In the next podcasts and on my Facebook pages and community emails, I'll be sharing with you more experiments you can do at home to test your own power. This is Lynn McTaggart, helping you to live the new science. Keep listening, and I'll continue to give you information and tips each time about how to incorporate this new and exciting information into your life.